Hi, we are familiar with WCF. In WCF, we can make our components and expose them as services, and those services offer different operations or methods that are exposed on different contracts. Clients can invoke these methods based on different channels: HTTP, NetTCP, MSMQ, or locally on through pipes. And the service obviously has to expose the contracts or the methods on a certain binding, and that binding tell us which channel or which format or which security options will be used when the client will invoke the method on the service methods. Now, based on different bindings, there are different configurations for each bindings, and how the message is formatted, how the message is delivered, and how the message is serialized and deserialized, how the security options work. All these things differ, and based on these differences, there are obviously differences in speed and efficiencies as well. On one binding, a method invocation could be faster than another binding. So in this video we will see the differences, like if we expose a service, same method or same contract on different bindings, what are the differences in the invocation of these methods, and we will try to identify like which is the fastest binding and why these differences are there. Before we straight away jump to this topic, let's first have a look on why we have come to these differences and what is the logic behind. Okay, we have been developing software now for many decades, and during all this time, one thing is common, and that common thing is like we always try not to reinvent the wheel. Like if we have written a software or a logic or a module that works well, and if it has solved a problem or it is doing something complex, or we have implemented a certain business logic, we want to reuse it. We try our best not to rewrite the same code. We try to reuse the code. That is common throughout the software development. Now to reuse the code, we have been trying different options. Like in the beginning, the people, when the object oriented concept came, the people started writing their classes. Say if one class implement a certain functionality, and the people would write that class, test it, and then would reuse the same class wherever it is needed. So one class handling one functionality, if it is written and tested, will be used in different modules of different projects. So that is in the beginning, like we had a class which is reusable component of the code. Okay, after now the problem with the the reuse of the class is like class is the source code. Say first version of a class came up and it was reused in different places. Then somebody found a problem in the code of that class. When the code is fixed, the places which were using these classes have to be recompiled now. If they're not recompiled and not deployed, the fix won't go with them, because once the project is compiled, it generates a binary code of all the classes that it consists of. So any bug fixed after the compilation is not included in that compilation or in that deployment. And also because source code is source code, it can be changed. So maybe in one project the same class was used and somebody had to do some tweaks, had to change something, so he will change. In another project, somebody else using the same class might do some other changes by copying the class locally. So there is a potential like same code can exist in small variations at different places. So there, after some time, there could be multiple versions of the same class, slightly different from each other. So the management of the code will become difficult. To solve this problem, we started using the lib files. Lib files are same as the classes, but the difference is like we generate or develop a class and then we compile it. When we compile it, we make the lib file. The lib file is not a source code, it's a compiled version of the source code, and for reusability we give the lib file to different people. If we say customer class has to be reused at different places, so we rewrite the customer class, we compile it individually, make a customer.lib file, and then we give lib file to each other. So that gives us better control to manage the originality or the fixes of the customer class. So whenever there is a fix, customer class exists, the source code exists at one place, the bug is fixed at one place, it's compiled again, and the lib file is given to all the places wherever it is reused. But still, all those places where the lib file is used, they have to, all those modules have to be recompiled and have to be redeployed. So we solved the management of the code with the lib files. But still, the problem is that whenever there is a change, all the modules which are using that lib file have to be recompiled. Okay, now to solve this recompilation problem, the idea of DLLs was brought in. DLLs are the same lib files, but they are dynamic libraries. So DLL, they are compiled not as a lib file, they are compiled as DLL files, and all the applications referring to the DLL files, they don't include or they don't need these DLL files. The idea is not to use them at the compilation time. At the compilation time, they just need to know, okay, which DLL file, which method, and what is the address of this method in the DLL file. What happens at runtime? At runtimes, that DLL has to be there in some folder, either in the subfolder where the application is installed, or in a central location like system or system32, the operating system shared folder. So application, whenever it comes to a point where it need to invoke a method of the DLL, it would go load the DLL at the runtime, give a call to the DLL method, and get the results back. So in this case, we now have in a way broken the link, broken the dependency of the lib or the class file at the compilation time. At the compilation time, when the code is compiled, we don't care what is the source code or what is the implementation of the method. We simply need the method details. What are the parameters, what are the details, and what is the address in the DLL. And when we come to the invocation, we load the file, DLL file dynamically, give a call, and get the results back. So we have solved certain problems like central management of the code, and then the problem with the lib file, like if there is a change, so it has to go and all the places or all the modules referencing to this lib file should have been recompiled. That is solved. So the DLL is the compiled version of the same class, customer class, which is not bound to the application which uses it at the compilation time. In fact, it is at the runtime when the code comes to know, oh, I need to invoke this DLL, so it loads the DLL, gives a call, and gets the results back. So in this case, our deployment or the fixes have become easier. Like if there is a fix that we have to do in the DLL, we will make the fix and we will only deploy that particular DLL which is changed. We don't need to redeploy the whole application. But again, it's not easy. For simplicity, I'm saying this, but it's not that easy. Because there are certain things that we have to take care. If the address that the DLL, the method, or all these parameters, we need to take care of all these things. But in simplicity, let's say that we only ship the DLL file which is changed. Now again, this has problems because say the same DLL one is used by 3 applications. the bug was found in application 1 and we fixed the bug for the application 1. Now the same DLL is used by application 2 and application 3 as well. We don't know the impacts of the fix that we have done for the application 1. It is possible like we fix something for the application 1, but because the same DLL is used by more than one application, so we might end up causing another problem in application 2 and application 3 because they are using the same DLL. So that is the problem that we refer like Microsoft System 32 Hell. And to solve that, they came up with the idea of the COM. Now COM is, in COM we have interfaces. So we implement certain interfaces and each interface has certain methods it's like Microsoft proprietary standard binary reusable component, and when we have a COM we implement certain interface and methods, and then we register that COM component into the registry of a system. And when some application has to invoke a method of a COM, we create the instance. The operating system provides certain APIs like co-create instance, and we instantiate the COM component using these API methods, and then we give a call. The advantage of the COM is like we can access this COM. The advantage is to make it more interoperable and more manageable. So interoperable in the sense like the COM component can be invoked from different languages. Like it should be invoked from VB, it should be invoked from C++ and other platforms as well. But it's easy to use it from Microsoft technologies. It's not that easy to directly invoke a COM component from non-Microsoft platform. Then the concept of the library file, classes, COM and DLLs. There is one thing common in all these kind of reusable things, and that is like whenever the application need to call or reuse this method. Now look at the memory. Each application has its own memory location. Whenever it loads a library file or a COM component or a DLL file, it has to load that component into its own memory space. Now when we pass the parameters like say customer to the customer class, say we say get customer, and we have to get a structure of the customer or a list of the customers. Now that customer list or the customer object exists in the memory space of the same application, and when we are passing these objects, we just pass the reference or pointer. So there is no problem in accessing the memory because the one application has the full control on its memory space. Now think of something like we have one application that has to invoke a method to another application. What is the difference? The difference is the cross application call. Within the same boundary, within the same memory location, passing variables or referencing variable, one module, another module, one class to another class, it's not a problem because it's within the same application memory. But when we have to invoke a function that where the component or the code is not loaded in the same application, in the same memory application, while it exists in the application in the memory of another application, then it's not that easy, and we have to do marshalling. And what is the concept of marshalling? The concept of marshalling is like if we have to pass the customer object to another application domain or another area of the application, another memory space, another process memory space, we have to package it. So the customer class or the customer object with all its attributes, we have to package it into a list of bytes or a byte array, or maybe as an XML, or maybe something that both sides know. Now we pass that byte array, that text or the XML to the other application, and on the other side that application doesn't know about this parameter or this byte arrays, it has to deserialize it. When it deserializes it, the same object is constructed into the memory space of another application. So the customer exists in one application. When the call goes to another application, we just pass the byte array or the XML, and the other application now does the reverse of the marshalling or serialization, and it deserializes to form the same object with similar properties and same data into its own memory space, so that it can do certain operations on it. When it does certain operations, it has to pass the results back. To pass the results back, it again does the serialization of the results, and the results come back to the first application, to the memory space of the first application, and the first application then again performs a deserialization on the response objects to form what the result has come. Now this process of marshalling is something that has a cost to it, and that is what we will talk about in this video. After the com and decom, now the decom was something like we were performing, we were making calls across application boundaries. So one application making a call to another application. And after that, we came up with the concept of services. The idea of web services came up, where we started sending XML messages over the web, and somewhere at uh, at a remote side, that XML message is received, and that XML message tells which operation to invoke, the input parameters, and then the other side would create the object of that component, pass all these input parameters, get the results back, and response, whatever the response is, it is again packaged into an XML envelope, XML message, and that message travels over the HTTP to the client side, and the client side reads the XML package or deserializes it to form what the result has come up. And this is these messages are called SOAP messages. SOAP is a protocol to use, and these days we're talking a lot about service oriented architecture, and in service oriented architecture we deal with services. So we consist big applications or enterprise level applications, or we make our business processes, and in these business processes at different stages we have to access different components of different systems, and if the whole thing is designed based on SOA, service oriented architecture, that means the one business implementation of one business process, we might be using many services, and when we call these services, all these calls are not in process calls, they are out process calls. These calls are made across the application boundaries, definitely, and most of the time they are made on a different machine, and sometimes over the HTTP as well, over the web as well. So serialization, deserialization is definitely there. That means the cost of marshalling the object or serializing the object and deserializing the object is there, and we have to pay that cost, and that cost means more processing time, because you have to read the whole object from memory, make it into a binary object, byte array, or make it as an XML or something else if you're using your own serialization protocol. And that is what we will talk about in this video. And WCF is all about services, and in WCF we can make our component, and that component is an interface which is implemented by certain class, and we can expose that interface, and when we expose that interface we can use different bindings that depends on our requirement. So here is an interface. Interface is iJob, and it has only two methods. Get job status, we just pass the job ID and it returns the status of a job. The other method is get new job. Now this one returns a structure, and that structure is like it consists of job ID, job status, and when the job is created. So it's just a simple structure, a class, just for demonstration purposes. Now when this method is invoked, get new job, When the response is generated, what happens is the server side creates a new object of this type, and it has obviously these properties, job ID. And now when this whole data has to travel to the client side, we have different options. One option is we make XML packet, and that XML packet, obviously if it is a SOAP packet, it has its own pattern or its own whole standard design, how this packet will be formed, what will be the nodes, and these add properties like job ID, job status, and the creation time. Are all the information are packaged into the SOAP message, and then this SOAP message is sent across the wire to the client side, and the client side then comes to know, okay, what are the details of the job. This is if we use SOAP or XML. There is another option. Another option is like we know this is a string. It will contain, this string might consist 100 bytes, 200 bytes, or whatever. Then integer consists 4 bytes or 8 bytes, and then similarly date and time have certain number of bytes that it takes. So we can serialize into binary as well. So that means whatever our string is, we take all the string characters and make a stream of bytes. Say our string consists of 100 bytes, so we take 100 bytes, start the object 100 bytes, and then we put 4 bytes for integer or 8 bytes for integer, then say 8 bytes for date and time. So 100 bytes, 8 and 8, 16. So 116 bytes is the blob that consists all the details of the job data. We pass these 116 bytes to the client side, and the client side knows how to deserialize it. So it knows exactly, like first 100 bytes are for job ID. So it takes 100 bytes, and whatever is in those 100 bytes, it takes them as a job ID. Then next 8 bytes, it knows, oh, this is the job status, and next 8 bytes is the creation time of this job. Now this is like is not a generic kind of pattern. It's a specific pattern, that only custom kind of pattern that these two applications, server and client, should know, and they can communicate. If some other application need to communicate with this kind of service which uses binary serialization, then it has to know how the serialization is happening. If it doesn't know, then it cannot communicate with the service. So these are the limitations of using different ways of serializing and derealizing. XML is standard. All the applications or all the parties know, oh, if it is using SOAP, that is how I will submit my request, and this should be the format to get the response. So SOAP is the standard. Now I have a service which implements the iJob interface, and it is a service contract and two operations, and one of the operation returns the structure which is saved data. It is a data contract, and it has 3 attributes. Now this is a job class that implements this interface, and let's come to the config file of this WCF service. In the config file, I have a binding comparison service, and okay, this is the class that implements the service, and I'm exposing this service on different binding. I'm exposing it on WcfHTTP binding, I'm exposing it on NetTCP binding, net named pipe binding, and then obviously the max binding to get the metadata. Okay, and I have a client, and in a client I initialize the client for all these bindings. So let me run this client so we get a better idea of what will happen. So this is the client to this service, and I can select which method to invoke, say get job ID, and I can select say how many times this method should be invoked. So I say invoke this method 5,000 times. So let me first initialize. So in initialize, I simply create the proxy, transparent proxy objects on all these different bindings. So I'm initializing WcfHTTP, NetTCP binding, net named pipe bindings, and now the proxies are initialized. So now if I make a call on WcfHTTP binding, and I say this method please invoke it 5,000 times. So okay, so it has hit the breakpoint. But what I'm doing here, in here I'm having a stopwatch object, and then I'm running a loop to invoke this method get job status. And then when the count is completed, invoke count, which is obviously uh, set here. So invoke count is 5,000 times. So after this, the stopwatch object will be created. The method will be, the service method will be invoked 5,000 times, and then stopwatch will be stopped, and we will get exactly how much time it has taken to make the 5,000 invocation. So let me run this. So now it is invoking this service, this operation of the service over the WcfHTTP binding, and this invocation will happen 5,000 times, and let's see how much time it takes. And we will exactly know the time in milliseconds and seconds. And after that, so it says total time for 5,000 invocation is these milliseconds, and they are 22 and 0.43 seconds. So 22,437 milliseconds. Okay, now I'm invoking the same method for the same 5,000 times, but on a different binding, and that's net TCP binding. Okay, same thing is happening in net TCP binding. So my invoke count is 5,000 times, and the client here using is net TCP client. Over there it was WcfHTTP client. All these clients or proxy clients are initialized. So, and again at then stopwatch is stopped and the time is displayed. So let me press F5 and we see how much time it takes on net TCP binding to invoke the same method on the same service but on a different binding. Okay, on net TCP binding, same method, same time, 5,000 invocations, and it has taken 6.8 seconds. So 22 or nearly 23 seconds on WcfHTTP binding, and 6 or nearly 7 seconds on net TCP binding. Now there is another binding, net named pipe binding, which we get out of the box in WCF, and that net named pipe binding is best if we are invoking the service on the same machine. So I have just pressed the button, and let's see how much time it takes on net named pipe binding. Okay, on net named pipe binding it is slightly lower than net TCP binding. So net TCP is 6.8 seconds, where net named is 6.5 seconds. There is small difference, but we can say it's a bit efficient than net TCP binding. Okay, I had this COM plus as well. So obviously the COM plus is faster than these net TCP and net named pipe binding. Now imagine a situation like the same component is, we invoke the same component from within the same process. When we invoke on WcfHTTP, net TCP or net pipe, we are making this call across application. So the marshalling or the serialization and deserialization does happen. All these calls, during all these calls, the request and response, they are packaged into a binary or XML packet and sent across to another application. The other application deserializes the message, acts according to the message, then creates the response into an XML or into a binary packet and sends the packet to the caller. But if we have the same component like get job ID class, and that is part of the process, we just refer it as a DLL or as a class, and then we say invoke get job ID 5,000 times, and you see how fast the result is. It has taken only 27 milliseconds. Huge differences than all these things. Now why, you can see this service is running on the same machine, the client is on the same machine. So when I'm calling the same method which exist in this boundary or within the memory space of the same process, it takes only 27 milliseconds to do 5000 invocation. But when I'm doing the same call on the same machine using NetTCP or net named by pipe binding, it is taking around 6 or 7 seconds. And the same method when invoked over WcfHTTP binding, it has taken almost 23 seconds. Now the difference, one of the major difference is like we know that when we expose a service on WcfHTTP binding and the client makes a call over the WcfHTTP binding, the request and the response messages are packaged as XML, and XML is huge. If we have to pass three properties, like in our case we are passing in fact in this method we are just passing job ID and it's an integer value coming back. Now let's call get new job ID, and if I call get new job ID, I am expecting a structure, a class or an object having different properties. Okay, so I will invoke get new job ID 5000 times. This should take more time because now it's a structure, it's not as simple. The request or response, the response packet or the response SOAP packet that is coming back from the service is now bigger than the first call, because it is a structure and it has certain 3 or 4 properties, and obviously to package those 4 properties it should take more time. So not a big difference, almost same difference, 22.88 seconds. And if I make the same call on NetTCP binding, and again it's 7 a bit more, it was 6 point something, no it is 7.07 seconds. And on net named pipe binding it is now 6.7 seconds. And when I'm invoking this method on in process, it's 85 milliseconds. It's a little bit difference, but we see the proportion or the ratio is almost same. So we were talking about why this difference is there. So on WcfHTTP binding we have to package the whole thing as a SOAP XML packet, and XML packet is huge. So we have to form up the document, XML document, parent node, and within the parent node in SOAP we have header, and the header has certain attributes that we pass, and then within the body of the SOAP we have to have a certain structure, and it's because these are XML, so we have to make up XML nodes and package all the data into XML. Now why this one is faster? Because we are passing the same structure across the application boundary into a different address space, into a different process address space. NetTCP is faster because Microsoft in WCF, Microsoft has tried best to make faster calls over the NetTCP. So if the service and the client are on the same network intranet, then the request and the response packets are not sent as XML packets, because XML is it takes time in terms of processing. Serialization and deserialization is not that efficient, while binary is faster because the size of the data that we send is small and serialization and deserialization process faster. So NetTCP packet, when it is serialized, it is faster, when it is deserialized it is faster, and overall the packet is small. So if this packet say if it is taking 2000 bytes, this packet for the same structure should be around 600 or maybe 500 bytes. So it's maybe 1/3 or 1/4 of what we sent in this. So that's why the time or the processing time that we save here is like serialization and deserialization. And similarly net named pipe binding, obviously the serialization deserialization might be almost same, taking the same, because we have already achieved the best performance in serialization and deserialization net TCP, but net named pipe binding is best is not the net is not on the TCP. It's using the pipes, and the pipes are efficient on the local calls on the same machine. So the time that we are getting is because we are using the pipes to make the calls on the same machine for a different component. And in process, we know the the component that this class I job is loaded into the memory of our client. So there is no marshalling, no serialization or deserialization process takes place. When we give a call to the job class creates a job object or job status object, and it simply send a reference to the client, because both the caller and the class are in the same address space. They both can access the variables because they exist in the same address space. So there is no transfer of the data that is happening. It's only passing the reference of these objects, and that's why it's much faster. And we can see the huge difference, like 23 or 22 seconds, and in here it's 7 seconds, and 7 times 3 is like 21. So we can see it's 1/3 uh, of what we processing time of what we pay on the WcfHTTP binding. And also, if we are talking about the bandwidth or the data that we are putting on the network, on net TCP we are not putting much pressure on the network. On WcfHTTP, yes, we are putting more pressure on the network as well. We are transferring more bytes on the network as well. But obviously, it doesn't mean like we should always use net TCP. All these bindings have certain advantages and disadvantages. We have discussed, we have to know our requirements exactly. Net TCP is only for intranet. So if we know our service and client will exist on the same network, we should not use WcfHTTP. If there is a certain reason to use WcfHTTP on the intranet or on the same network, fine. But if there is no particular reason for WcfHTTP, then we can go for net TCP if we know our client and server are on the same network. And if for some reason we know there is some client that has to exist on the same machine where the server side is installed, then we should use net named pipes binding, which is even faster than the net TCP. Not big difference, small difference, but can add some value. And if there is no need to make a service call, then obviously the in-process call, by just referring to the assembly or making a class into the same project, bringing the class into the same project, referring the class into the same project, and then making a call, is definitely faster than everything. So we have to go through our requirements, and we need to see what are our requirements and which binding suits us. Say if there is a requirement, I haven't brought the binding which is basic HTTP binding. If we have a certain requirement, like, oh, there are some old clients and that have to make our calls like they were using maybe ASMX like service, and for these kind of issues, or we want to make it open so that anybody from any platform, Java or any other platform, can come and make a call to our services, then basic HTTP is very simple. So we should expose our service on basic HTTP, but we do not have certain advantages that we get in WcfHTTP binding, like passing transaction, security related stuff, and compensation and these kind of stuff. We don't get on basic HTTP binding, but basic HTTP binding is better if we want to offer full interoperability on our services. So bottom line is, these bindings like basic and WcfHTTP binding offer us flexibility, generalization, but there is a price to pay, and that price is the time or the data that we put on the network for the transfer. So if we do not have a real reason to go for basic or WcfHTTP binding, then net TCP binding and net named pipe binding are best. But for them, For these things, our server and client has to have on the same network. We can make our custom binding as well. Say we know, so there is a reason that our service doesn't have to be on the same network, so we have to make a call on the internet, but we want to make it faster. Then the one option that we have is we come up with our custom binding, and in that custom binding we say, okay, we are not transferring our request or response using SOAP, but we do the serialization and deserialization into binary, and we pass the binary data over the HTTP protocol or HTTPS protocol to the server side, and over there we deserialize the binary, make a call, package this response into the same way into binary format and transfer it back. So but that binding doesn't exist. We can make a custom binding, and that will be faster. So it will be a combination of HTTP basic or WcHTTP kind of binding, but will offer us faster serialization and deserialization process. So we would be able to make a call over the web, but with a faster serialization and deserialization. In the next video, we will see what are these packets that are sent across on these different bindings, and we will really see what is the value and why these packets are small or large.